Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Suhail Dhawan with us today. Hey, Suhail, how are you?
I'm good.
What's your geolocation?
So I am currently in New Delhi, but I'm a postdoc at the Oscar Klein Center in Stockholm for another 10 days. At which point I moved to the IOA and Kavli Institute in Cambridge. And I'd say move to because it is going to be physically impossible to get any mode of transportation into the United Kingdom for a while, given all the regulations. So I guess I would say I have contractually swapped. That would be the appropriate thing to say.
Right. But geo-wise, you're in India. Let's see, and so it is nighttime there.
Yeah, it's about 9:30.
Very good. Yeah, it's about 9 in the morning here in Phoenix, and it's looking outside here. It's going to be a typical horrible day in Phoenix. It's blue sky, it's sunny. It'll probably heat up to around 70 F. Which I could do a quick conversion to centigrade if I had to. But it's very pleasant. So what is it's still winter in India. So what is winter like in India? Where you're at?
I mean, yeah, it's quite diverse because like the north does see quite a lot of winter, and this is actually one of the myths that takes me a while to explain, specifically in mainland Europe, is that Delhi winters are winters. Because one, it gets like below 5 degrees at night. So it's about mercury's below 10 degrees centigrade.
Yeah.
And that's outside. So it's inside, it's about 8 degrees because, house is not built for that weather, which is, I guess, why I'm wearing the hat and everything. And I'm like, I need to get clad because, indoors is what really hits during the first week of January, or like the first couple of weeks of January. And like it's been quite bad this year. Like it got cold from October onwards. So yeah, it's been a particularly special winter that way. Yeah, it's like my own thoughts have frozen a little bit.
Yeah. Well, it's probably still warmer in Stockholm.
Yeah, no, that's true. And I think there's definitely more daylight. And I kept a track of Stockholm for some reason because I still had hopes that I might move. And I didn't have a lot of sunlight for maybe 4 weeks at a stretch. And that was, even by like the 4 winters I spent there, it's a bit much, I think. So, yeah.
Takes definitely a little getting used to. Yeah. Well, congratulations on your new position. Eventually you'll get there. Hopefully sometime 2021. But we shall see. So Suhail, what do you like to do for research?
Right. So I'm very excited about doing cosmology broadly with exploding transients. So I'm interested in currently, or what I've been doing is mapping the expansion history, both in terms of the recent phase of accelerated expansion, but also the present expansion rate of the Hubble constant using type 1a supernovae, also electromagnetic counterparts to gravitational wave sources. And I'm very excited about lens transients, specifically lens supernovae. So this is more at the sort of characterizing them, getting time delays, looking for more lens supernovae and transient surveys. So I try to come up with like a cool phrase, but I'm not inherently cool. So I think of it as like cosmic lanterning, and I'm hoping that catches on.
Yes.
Yeah. So yeah.
Awesome. And that is going to take us to this really lovely APJ article on cosmological model insensitivity of local H0 from the Cepheid distance ladder. And Suhail, take us away.
So I guess before diving into the article, I just thought a bit of context for why this is exciting and what was like both the general and the specific question we wanted to address and how we wanted to go about answering it. Okay. So over the last like few years with improved precision in measuring the present-day expansion rate of the universe, or the Hubble constant, there's been an observed tension between the direct measurements from local measurements, like the local distance ladder, using various different combinations, and the value inferred from the early universe, typically like using the cosmic microwave background plus like systematics checks with other probes. And I think this is quite interesting because it could be a hint of new exotic cosmological physics. And there's also debate within that for what it could be. So I don't think like it's any, like, I think there's quite a lot of debate also about like, what could that new cosmological physics be? And people are trying to see like, is that late universe or early universe physics? And there's not really like a convincing model that would stand out, I would say, broadly in the literature. But also, it could be something that's like unknown sources of systematics or something in the way that either one of these measurements is done. And I think given, say, what's at stake, it's particularly interesting to scrutinize different aspects of the individual measurements and the observed tension, as well as like moving forward with independent probes. So I looked at different parts of the local distance ladder measurement in previous studies. And what I was interested in was particularly understanding the role of the cosmological model assumed when making the local Hubble constant measurement, and how that weighs in to the tension and to future H0 measurements. So essentially it came from the fact that a lot of times, like, this is bouncing ideas off of people at conferences, people would say, okay, so like the local distance ladder, the way it sort of works is that it calibrates the luminosity of type 1e supernovae. Bright stellar explosions are interesting because you can see them to like gigaparsec distances, so they're very like useful and robust for cosmology, and also you can standardize the peak luminosity to get robust distances.
Yes.
But when looking at measuring H0, typically the distance ladder is cut at like a redshift 0.1, 0.15. And the idea was, okay, because that redshift range, type 1e supernovae, are not sensitive to particularly like second order derivatives in the Taylor expansion of H of Z. So for example, the deceleration parameter, it's fixed to a certain fiducial value.
Right.
However, that fiducial value itself comes from things like the high redshift type 1e supernova Hubble diagram, or like magnitude redshift relation, along with, of course, other probes that have been robustly developed to precisely measure properties of dark energy. But typically, the way in which that measurement is done is by comparing low redshift type 1e supernovae with higher redshift type 1e supernovae. So there's some amount of like covariance in the twice counting of this like local nearby Hubble flow type 1e supernovae. And essentially, like instead of inputting a value of Q0 from the high redshift and then doing the distance ladder, what we wanted to see was, can we account for a simultaneous inference of both properties of a cosmological model at higher redshift? So by taking every type 1e supernova that we have that can be on a magnitude redshift relation, and seeing, under various different assumptions of what could be the properties of accelerated expansion, what do we infer for the value of the Hubble constant without having this truncation as is done in the distance ladder?
Okay.
So I guess figure 1 and 2 would be like a nice way to start to show what we were trying to do. So
I just want to look at something.
Yep.
Okay, very good. Just checking something in. Okay. I'm just looking at equation 2 there. SINN? Is that a typo?
Oh no, so that's the Singe function.
Ah, it is a Singe. Okay, that's what I thought. But it says SINN, so threw me a little bit there. Okay, figure 1. All right, we got set lots of that up. Let's take a look at figure 1 and 2.
Awesome. So basically, I wanted to start from this because So I wanted to focus on both the expansion history constraints as well as the constraints in the Hubble constant. Then I'll like go through the details of what went into this to get the inference. So essentially, if we take what is the probes of the expansion history, like high redshift type 1 supernovae, BAOs, and CMB, we have lots of different explanations for what could be causing this late phase acceleration. Typically, we would say like the most favorable one is a cosmological constant, but there's a lot of different physical motivations that, based on like a combination of the expansion histories, have not been excluded, and they're all like viable explanations of current data sets. And this also like motivates partly why we want to do things like the Rubin Observatory and Roman Space Telescope to improve those constraints and start to exclude certain models. But these are all viable explanations. We were like, okay, let's start with a suite of different models. They have lots of different physical explanations. So I just go through everything in the legend just so that like we can get a feel for what these different models are. So like a WCDM is just a phenomenological extension of the lambda CDM model with the equation of state and dark energy being a free parameter. Okay. So a biometric gravity model is is a massive gravity theory where typically when massive gravity is thought of, there were these Boole where there's a ghost modes that would exclude these models, but having a second metric with a carefully constructed interaction term can get rid of these ghost terms, and these could be viable models, and they are self-accelerating, so we get accelerated expansion without an explicit cosmological constant. Okay. And the different like interaction terms turn on and off. And there was an associated paper that we did like a couple of years before on like cosmological causes of attention. And that's where we detailed this particular model, which has this first order interaction term that is turned on. And so that is not overly complicated to fit the data too much. And it's not like overly simplified such that it gets like very simply excluded by being very different from lambda CDM. Then we have like slow roll models, which are like inspired by inflation-like physics, but at late universe stage. So that's where you essentially have like this dynamical dark energy behavior. And then the algebraic thawing, which is the next model, we essentially have these dynamical scalar fields, which are quintessence models. So we have more positive than -1 equation state. Then we have growing neutrino mass models, which are designed to solve the cosmological coincidence problem, where essentially it's the why now problem of why is it that despite different dependencies on the scale factor, we still have similar order of magnitude for the matter and lambda densities. And this essentially does that by giving it sort of like a natural epoch where by tying the mass of the neutrino to the acceleron field, the epoch at which the neutrinos become non-relativistic is essentially when we would start expecting that the density is similar.
Okay.
Now, all of those models essentially having some sort of smooth behavior, and that's what you can see, which is the Hubble residuals for each dark energy model relative to best fit lambda CDM. And the last two models essentially designed was, so they were designed to sort of explain accelerated expansion. And the aim was to sort of have these very rapid transitions at low redshift where, you know, they wouldn't be testable because those are not typically supernovae, like at 0.02 or below, those supernovae would be removed from a Hubble diagram because of high uncertainties, peculiar velocities. However, because we have the calibrators along with the high redshift type 1e supernovae, so calibrators by definition are redshift 0, because what we're looking at is just distances and magnitudes. Then we essentially have like a constraint below the transition redshift in these models. And we can see like how well these models are doing relative to something like standard lambda CDM.
Mm-hmm.
What I think is interesting, and I'll just touch upon it now, is that we see that all of the low redshift supernovae are a bit preferentially brighter, and that might be slightly just based on a delta chi-square favoring these transition models, while all other models are more or less giving similar higher redshift expansion history predictions. And this could be because of unknown sources of systematics, but this is why like people are currently looking at doing things like this wiki transient facility, low redshift type 1e supernova survey, as well as other surveys like Assassin Foundation, where we want to have like a very homogeneously calibrated sample of type 1e supernovae at low redshifts, which is very counterintuitive because we'd expect that like at high redshifts is where like we're having troubles, but given that like those are very uniformly observed samples on a very well understood system, that's like not where the photometric calibration is at the highest importance in the systematics covariance. It's actually wanting to get it done well at the low redshift with a homogeneous sample that is all done on like a single system where we understand like selection effects, photometric calibration. That's something that's what's interesting. So I think like hints of some sort of delta chi-square that is maybe suggesting it could be something like this is interesting. And I think it's something which we can actually with oncoming surveys be able to answer more definitively whether this was just something that is like a fluke because of systematics. So can we actually have certain constraints on the presence of some such exotic dark energy models? So that is like in terms of what the status of these different models and how they are constrained with current data is. And so from figure 2, I think would be, I should do figure 2 and then probably describe a bit on what goes in section 2. Okay. So figure 2 is essentially where we looked at, so those were like model predictions. We can essentially do nearly every one of those models with like the high redshift part. So sort of we need the calibrators because a priori, we don't know the absolute luminosity of type 1e supernovae really well, like say from theoretical models. So we need a calibrator like the Cepheid variables. Yes. And essentially, that's what gives us the constraint on the Hubble constant. Now, here, there's been a detailed study of the systematics covariance matrix between the 19 type 1e supernovae that have a Cepheid host galaxy, yes, and the ones that are in the Hubble flow. So typically, typically the way it's done in the distance ladder is only till the nearby Hubble flow. But here's looking at all of the type 1e supernovae. And in our fiducial case, so I think one way to illustrate that is looking at the 3 blue curves here. So the lambda CDM value here is essentially just assuming statistical uncertainties on the distances and just taking a calibration that matches the shoes value. So we basically took the starting point as being the shoes calibration of the type 1 supernova luminosity from Reese 2019. Okay. And then essentially just got the absolute, like the value till we got like H0 that matches that. So essentially the measure here is to see how much is the delta shift from that fiducial assumption when we go from doing the distance ladder, which is essentially the dashed line in the middle, to doing the full systematic covariance matrix between all of the supernovae, both in the calibrator and the Hubble flow sample. Okay. And there we can see like the dashed line and the solid line really don't have a huge shift. So that's just like the different approaches. But the sort of solid blue line is what is the fiducial lambda CDM value when we do the fit to the entire sample. Right. And then we start to relax that assumption and we just say, what if dark energy could be any of these things? And while we see that like in the previous plot, there is this slight possible sort of transition or like there's some behavior that could be odd at low redshift, between these different models, which are very different from their physical motivations, we don't see a shift in H0 that is like comparable to the size of the tension. The difference in between the highest and the lowest is about 0.47 kilometers per second per megaparsec. So that's something which is showing that that assumption on the input is, or like the assumption of the dark energy model that is taken as the input here is not a dominant way of shifting what we infer as the value of the Hubble constant. Now, it's also, we wanted to see, okay, what if we didn't have the systematics that are plaguing the measurements. And I guess I'll just quickly mention what the difference is, and then I can say what all goes into that.
Okay.
And go that way. So the dotted line is statistical only, the solid line is with systematics, and that shift is about 0.8 kilometers per second per megaparsec. It's a bit bigger than the other shift, but it's still not at the same size of the observed tension. But it would be something which is interesting when we're getting to that 1% level of the distance scale. So we want to have like a better understanding of what these systematics are. And I guess what goes in, maybe that's best, like we can show that from the description of section 2. So
Okay.
I guess 2.1 should be the best way of. Yes. So I think if you just scroll down, there's different sort of bits of the calibration or bits of the systematic uncertainties. So one of it is coming from modeling the photometric calibration and the CalSpec calibrations. This is following on from the state-of-the-art Pantheon compilation by Skolnick et al., as well as following the summation of how the covariance matrix is done by using the beams with Bayesian corrections approach that has been used by the Dark Energy Survey. And the different sources are like photometric calibration, then using this sort of host galaxy mass bias. So this is essentially the relation that was found, I think it's early, maybe the late 90s, early 2000s, that the luminosity of type 1e supernovae depends on the properties of the host galaxy. So essentially, brighter supernovae would preferentially exist in younger environments that are also less massive. But if you correct for, if you correct for the stretch and the color, which is the two typical standardizations used in cosmology, that relation flips. And that's for the entire underlying population of type 1e supernovae, which is what people try to model and what we're saying we'll be seeing when we're doing dark energy measurements. But one thing to note here is that this is Cepheid calibration of the supernovae. So what we're trying to see is what would be the extent of systematics if the host population of the calibrator supernovae didn't match that of the Hubble flow supernovae. Okay. And that's what we've added into the covariance matrix, along with other things like what is the origin of the intrinsic scatter of type 1e supernovae, because even after the standardizations, we have about a 0.1 to 0.12 mag scatter. And is it purely coherent? Is it coming from the color terms? And that's something where, there's two different prescriptions in adding systematics from that, as well as things like Milky Way extinction and modeling systematics because of the heterogeneous low redshift type 1e supernova sample. So all of that goes into basically that final term of about 0.8 kilometers per second per megaparsec in the shift in the value of H0. So that would be interesting, want to understand what's actually causing the host galaxy mass step. So I think whether it's coming from dust or something intrinsic, that's something that's up for debate. And there's with larger samples and with more refined analyses, we're getting to try and understand, can we say it's one way or the other and then model it when doing cosmology with future surveys. And one of the things is we're looking at doing it with untargeted surveys, because then we're essentially going to probe the underlying distribution of the environmental properties, as opposed to targeted surveys that'll only look at a part of the underlying population. So that's something that would be interesting in the ongoing ZTF plus LSST plus PanSTARRS plus other untargeted surveys era, which I think that would be very interesting, both from cosmology and from one a progenitor's point of view. So moving to I guess figure 3 which would be sort of what we wanted to do next after looking at the different models. Right. So this was under different dark energy model assumptions. So we said, okay, we don't know what dark energy is. we essentially are fitting different models from various different physical motivations, we don't find any difference. But what if we just fitted for the Taylor expansion of the Hubble parameter as a function of redshift, and essentially just fitted for H naught versus Q naught, what is the level of correlation we get, and essentially what is the value of Q naught when we do everything simultaneously instead of taking Gaussian prior on H naught and then fitting Q naught, or like fixing Q naught and then doing H naught. What we find is that it's actually not deviating from the fiducial values. It's minus 0.59 plus minus 0.14. And I think with future analyses, this uncertainty is expected to dramatically improve. But even when we're completely agnostic to what like the energy densities are, we still don't find like a huge shift in the value of H naught. It's almost exactly that of the fiducial case in the what we call the stat plus cis cut z, where we essentially have just a shoes-like covariance between calibrators and nearby Hubble flow. But here, in all of these cases, because we're fitting Q naught, we take all the supernovae, we just do a covariance that's similar to shoes. So we say, okay, if we didn't have any covariance between like the calibrators and the very high redshift, would that be a big difference? We don't see a huge difference. We just see that the uncertainty on Q naught is a bit smaller because then we have fewer covariances that are driving or blowing up the contours for on the x-axis there. So it's showing that like under different situations, of course, we get slightly different uncertainties on Q naught, but it doesn't change what the inferred value of H naught is. The table, sorry?
Yeah, I'm with you.
So the table on the right-hand side is us taking each individual systematic contribution, both in terms of the contribution to the uncertainty and the contribution to the shift, and essentially just going through this where, so this was computed by Tim Brout and Dan Skolnick, where they were essentially taking the framework from the state-of-the-art high redshift supernova surveys and like quantifying the photometric calibration uncertainty, which is still like the most dominant, but also understanding the intrinsic scatter model is important in order to like get better uncertainties when we get to the percent level. And when we start improving like the first and second rung of the distance ladder, as we start seeing already with the Gaia EDR3 improving the first rung, and we expect that there's going to be more Cepheid calibrators. And when it gets to a comparable level to the supernova systematics, so the 0.8 is going to start to matter, and then we want to understand what is causing the intrinsic scatter, what is the SALT2, which is the template model that we're using to fit the light curves, like what is that error flow contributing? How can we improve upon that? How can we improve the light curve model by using things like a PCA decomposition or having like spectrophotometry as the input? And can we go in a model independent way? That would be things to improve when like we're getting to that precise value of getting to the percent level on the distance scale. So I think that's quite exciting because it's also coming from like both understanding instrumental calibration, but also like the physics of type 1e supernovae and their intrinsic population and their environmental properties. So I think that's quite cool because that would really help improve systematic uncertainties when we're trying to get to that level of saying, are we seeing new cosmological physics? So that's something I think is quite interesting to know which are the dominant sources of this era.
Yeah.
And it's also nice to see that like there isn't a huge shift in the value of H naught based on any individual calibration source. So it's not like one of them is shifting them in a very large way. It's just like a few sources that are just having a delta shift, which is important to understand when looking at future shifts.
Yeah. Very cool. Very cool. Very cool. And we kind of say that here at the end. So very nice. Awesome. So you hinted at it a couple of times as you walked through the paper. So what in your view are some of the next steps that the community could take? Are there new observational stuff coming down the pipeline? Is there yet additional cosmological models that one should consider in this? Just sort of where do we go from here, given your article?
So I think there's a few things that I'm very excited about. So having completely independent probes of H0, both local and early universe. So like this has been done in early universe with like Big Bang nucleosynthesis, but having like independent local probes of H0. So I'm excited about lens supernovae. I think that would be super cool just to have like, I mean, lens supernovae in general, I think just super cool for whether testing weak field limits of GR or like just, understanding cores of elliptical galaxies, extinction, high redshift, but also like using time delay distances to measure H0. And I think one thing that's interesting is they're very complementary to lens quasars because them being standardizable candles, we can use the fact that we know the intrinsic luminosity fairly well relative to quasars to break systematic uncertainties like mass sheet transformation, but also like we'd have like if caught early, then we can also use the multi-wavelength light curves to reduce systematics from microlensing and essentially just monitor them for a short time period. Of course, they're rarer, so there's a flip side. That's why I say it's complementary. So I think there's a lot of like cool stuff where in both the ongoing transient survey and LSST era, finding and like observing them with ground-based AO as well as getting light curves from Hubble's and GWST would be something that would be exquisite in order to shed light completely independently on the H0 debate. I also think like low redshift type 1e supernovae are extremely exciting for large-scale structure studies.
Yep.
So like I think it would be really cool to like have constraints on like bulk flows from large samples of nearby type 1e supernovae, and also how that would weigh into improved constraints on dark energy. And I think it would be related like to directional dependent Hubble constant, and just have like if we have 2,000 supernovae spread across the sky, essentially get like 10 Hubble diagrams on any side. And that would be nice to see. So yeah, and it would be really cool in the extremely large telescope era to push like maybe also like if we have Cepheids in the Hubble flow or like TRGBs in the Hubble flow, any of the secondary indicators in the Hubble flow.
Right, that would be cool.
I think that would be cool. Yeah.
Future's bright. Future's bright. There's lots of exciting capabilities and new data coming online. So it'll be a really interesting next 5 years in this topic. It's great. Super duper. Suhail, I want to thank you so much for spending some time and walking us through your lovely article today.
Thank you for having me.
All righty. Thank you, everyone, and we'll see you on the next one. Bye-bye.